All right, let's jump right in. We're going to connect a math puzzle that's literally centuries old to the absolute cutting edge of artificial intelligence. And it all comes down to one big idea: the power of abstract thought.
So, here's the big question. What in the world connects a 350-year-old math puzzle to the future of AI? I mean, these things seem worlds apart, right? Well, it turns out the answer is all about the hunt for hidden patterns, for structure.
In our story, it doesn't start in some shiny modern data center. Nope, we have to go way back to the 19th century with this incredible, brilliant attempt to solve one of the most famous math problems ever.
See, to tackle Fermat's last theorem, mathematicians got creative. They invented this powerful new tool, creating these abstract number systems they called rings. You can think of them as these little pocket universes with their own special rules for adding and multiplying. And for a hot second, it looked like they'd done it. They thought they had cracked the code.
But then came the twist. The proof, it just collapsed. And the reason why is actually super interesting. You know how with regular numbers, like the number 12 is always 2 times 2 times 3, and that's it? That's called unique factorization. Well, it turns out these newfangled rings didn't always play by that rule. But here's the thing. This failure wasn't the end of the story. Not at all. It was actually the beginning. It forced everyone to dig way deeper and really understand the rules of these bizarre new worlds.
Okay, let's hit the fast forward button and jump to today. Because we're facing a really similar challenge, just on a totally different scale. Instead of hunting for patterns in number theory, we're trying to find structure in these massive, ridiculously complex data sets. And our tool for the job? The graph.
So, what exactly is a graph? Just think of it as the ultimate game of connect the dots. You've got your dots, which we call nodes, and the lines that connect them, which we call edges. It sounds simple, right? But this basic blueprint is how we map out, well, pretty much everything, from who your friends are to the entire structure of the internet.
Just look at this. I know it kind of looks like a spider web from outer space, but what you're actually seeing is a map of the internet's backbone. Each one of those dots is a whole network, and each line is a connection between them. A graph like this lets us see the hidden clusters, the big superhubs that hold the whole thing together.
And it's not just for big things like the internet. This same idea works on a microscopic scale. Take chemistry, for instance. There's this famous dataset called mutagenesis, where every single molecule is drawn out as a graph. The atoms are the nodes, and the chemical bonds are the edges. And by looking at these structures, an AI can actually learn to predict if a compound is going to be toxic or not. Pretty wild.
And then, of course, you've got the big one, the biggest graph of them all, the World Wide Web. Every single web page is a node. Every single hyperlink is an edge. When you think about it, understanding this giant, sprawling structure is literally what makes a search engine work. The scale is just, it's hard to even wrap your head around.
Okay, so we've got our map. We've turned our world into a graph. We can see the structure. But now what? What's the next step? How do we actually teach a computer to understand the rules of the game, the logic that's driving all those connections?
Well, that's where this field of AI called inductive logic programming, or ILP for short, comes into play. The best way to think about it is like you're teaching a machine grammar, not for English or Spanish, but the grammar of relationships hidden in the data. It learns these logical rules just by looking at tons of examples.
And here is a classic, super simple example. The rule says, X is the grandparent of Y if X is the parent of some person Z, and that same person Z is the parent of Y. See? It's just a clean, logical rule. It's something we humans get instantly, and it's exactly the kind of thing an AI can figure out on its own, just by looking at a bunch of family trees.
But here's where we hit a snack. Remember how those 19th century rings didn't work out because they weren't as neat and tidy as regular numbers? Well, guess what? Real-world data is exactly the same. It's messy, it's got missing pieces, it's full of mistakes. In the field, we just call all that stuff noise.
And that brings us to the hero of our modern story. It's a new AI system called Glider. Now, the full name is a bit of a mouthful, but the big idea behind it is actually pretty elegant. It learns these logical rules in a way that's much more flexible, more resilient, and it's all inspired by the structure of a graph.
So how does it pull this off? Well, let's take a look. An older system might learn a very rigid black and white rule like, a person is suspicious if they don't have an ID. Simple enough. But Glider is different. It learns this concept as a flexible graph. It understands that being suspicious isn't just one thing.
It's connected to multiple factors, like maybe having a criminal record or being linked to another person who's also suspicious. This way of thinking, this graph-based approach, makes it so much better at understanding how things are connected in the real, messy world.
And here, this is the payoff. This chart shows what happens when you start throwing bad data at Glider. That bottom axis there, that's the percentage of wrong information we're feeding it, all the way up to 100%. Now just watch those performance lines. Even when 50% of the data is flat out wrong, its accuracy stays incredibly high. It's literally finding the signal in all that noise. That is what we call robustness.
So let's tie this all together. We started this journey with a failed math proof, right? Pure abstract stuff. And we've ended up with an AI that can think its way through total chaos. So what's the real connection here?
You know, I love this little anecdote from a math forum. It's about a PhD student who builds this huge, beautiful, abstract theory. And then, at his defense, the examiner asks for just one simple example. And it turns out the only example that works is the most boring, trivial one imaginable. The whole thesis just implodes. And the point is, abstraction is incredibly powerful, but it has to connect back to reality. It has to actually describe something useful.
And that's the link. That's the whole point. The mathematicians who came up with ring theory after that failed proof, they were looking for the deep, underlying structure of numbers. And the engineers who built Glider today, they're looking for the deep, underlying structure of data. It is the exact same quest, just separated by about 150 years.
This ability to just step back for a second, to see the simple, abstract graph hiding underneath all the messy reality, it's one of the most powerful tools we have. It's what lets us find that signal buried in all the noise. And it really makes you wonder, doesn't it? What other hidden structures are all around us right now, just waiting for us to figure out the right way to look?